Hello everyone, welcome to this new PDC lecture series. In this lecture series, uh, we will demonstrate the Bode diagram of a simple system with some given examples. So let's start with Bode diagram. So what is Bode diagram? This is a pair of plots which represent how the log of amplitude ratio varies with the frequency omega and how the phase shift varies with the frequency omega. So in this lecture, let's start with first order system. First order system. So let's say we have a system G of S equal to 6 to S plus 1. So this is your first order system, and now we have to plot the Bode diagram for this system. So plot the Bode plots for system as per equation 1. So to plot the Bode diagram, first we have to find out the amplitude ratio. So step 1, find the expression for amplitude ratio as a function of omega and phase shift phi as a function of omega. So to do so, first put S equal to j omega into equation 1. So here we will get g of j omega. Let's say this is z equal to 6 upon 2 j omega plus 1, and this will be equal to 6 upon 1 plus j 2 omega, and this will be equal to 6 1 plus j 2 omega inverse, and this is another complex number, let's say z1. So 6 z inverse. So using the property z inverse equal to z1 inverse equal to z1 conjugate upon z1 mod whole square. So using this property we will have 6, so z1 conjugate, so z1 conjugate will be 1 plus j 2 omega conjugate upon the mod of 1 plus j 2 omega whole square, and this will finally we will have 6, and the conjugate of, so the conjugate of 1 plus j 2 omega will be 1 minus j 2 omega upon 1 plus 2 omega whole square, and this will be equal to 6 upon 1 plus 4 omega square, 1 minus j 2 omega. So this is capital G of j omega. So to find out the amplitude ratio, we will have the mod of G of j omega or mod of z. So therefore we will have square root of the real part of z whole square plus imaginary part of z whole square, and that will be equal to under root 6 1 plus 4 omega square. So this is the real part square plus the imaginary part is minus 2 omega, or 2 into 6, that is 12 omega, 1 plus 4 omega square whole square. So finally we will have square root 1 plus 4 omega square whole square 36 and minus 144 omega square. So finally we will have so 36 common, so we will have 6 common, 1 plus 4 omega square, and here we will have 1 minus 4. So 1 plus 4 omega square, and that will be equal to 6 upon under root 1 plus 4 omega square. So therefore amplitude ratio is equal to 6 upon under root 1 plus 4 omega square. So this is equation number 2. And the phase shift can be calculated as the argument of z or argument of capital G of j omega. So therefore tan inverse the imaginary part of z to the real part of z. So we will have tan inverse, and the imaginary part is minus 12 omega. So minus 12 omega upon 1 plus 4 omega square. And to the six upon 1 plus 4 omega square. So we will have tan inverse. So this term gone. So we will have minus 2 omega. So phi equal to tan inverse minus 2 omega. So this is equation number 3. So we have calculated AR omega and phi omega, and the next step is take log 10 of AR omega. So from equation number equation number 2 we have AR omega. So let's copy this. So let's copy this. So taking the log both side, we will have log 10 of AR equal to log 10 6 minus log 1 plus 4 omega square 1 by 2. So log 10 AR minus log 10 6 will be equal to minus half log 10 1 plus 4 omega square, and this will be equal to log 10 of AR upon 6 minus half log 10 of 1 plus 4 omega square. So this is expression for amplitude ratio after taking log 10, and this is equation number 4. So we have equation number 4. So the next step is step 3. Plot the gain plot. Plot the gain plot and phase plot. So let's say we are interested to plot AR upon 6 versus two omega. On log 10 log 10 scale. So here let's say we have 1. So first we have to find out the low frequency asymptote. So low frequency asymptote. So at low frequency asymptote, the omega tends to 0. It means 2 omega tends to 0, and 2 is the time constant of the system. So it means omega tau tends to 0. So using this expression 4, we will put two omega square tends to 0. So it means this second term tends to 0, and we will have minus half log 1, and that will be equal to minus log 1. So it means AR upon 6 will be equal to 1, or AR will be equal to 6. So at low frequency asymptote, so therefore at low frequency asymptote we will have omega tends to 0. It means AR by 6 tends to 1, or AR tends to 6. Second, high frequency asymptote. High frequency asymptote. So at high frequency asymptote, omega tends to infinity. It means omega tau, that is 2 omega tends to infinity, or 4 omega square tends to infinity. So using expression 4, so using equation 4, so this term is very large, so I can neglect the first term. Therefore we will have minus half log 10 of 4 omega square, or 2 omega whole square, and here we will have minus log 10 of 2 omega. Here 2 is the time constant of the process. So the equation for the high frequency asymptote is log 10 AR by 6 equal to minus log 10 of 2 omega. So the slope of the slope of 4.1 line 4.1 equal to minus 1. The contribution from the high frequency asymptote for the first order system in the slope minus 1. 3. Corner frequency. So the corner frequency when omega is equal to omega c, and this omega c is corner frequency. So this omega c is corner frequency. So when omega is equal to omega c, we have omega tau, that is 2 omega equal to 1. It means omega c will be equal to 1 by 2, that is 0.5. So the corner frequency for this system is 0.5. So using 4, so at corner frequency 2 omega is equal to 1. So 2 omega whole square is equal to 1. So this is 1. So therefore at corner frequency the equation 4 gives minus half log 10 of 2, and that is equal to log 10 of 1 upon under root 2. So therefore AR by 6 at omega c will be equal to 1 by root 2, and that will be equal to 0.707. So this is equation number. So this is equation number. Let's say 5. So for part B we have to plot the phase shift. That is phi versus omega tau, or in this case phi versus 2 omega. So again at the low frequency, so at omega tends to 0 or when omega tau lies between 0 to 1. So in that case phi can be calculated using the equation number 3. So here we will copy equation number 3. So using equation number 3, using equation 3, we will have so here in this case tau is 2, right? So when the omega tends to 0 means 2 omega lies between 0 to 1. So in this case we will have this tends to 0. So phi will be equal to 10 inverse minus 0, and that will be equal to 0. Similarly at omega tends to infinity or when omega tau is lies between 0 to infinity. So again for the present case tau is equal to 2. So when 2 omega is lies between 1 to infinity, so we will have so in this case this phi will be equal to 10 inverse minus, and this 2 omega will be equal to infinity. So it means minus 10 inverse infinity, and that will be equal to minus 90 degree. Again at omega equal to omega c, and that is equal to 1 upon tau 1 upon 2. So when omega equal to 0.5, so in that case In that case phi will be equal to, so in this case phi will be equal to tan inverse minus, so this omega tau is equal to 1, and that is minus tan inverse of 1, and that is minus 45 degree. So using this information we can finally draw the Bode diagram in the next slide. So let's draw the Bode diagram as follows. So here we will have y-axis and here we will have x-axis. So let's say this is omega tau, and in this case let's say this is 2 omega, and this is AR by 6. So here we will have another plot for the phase plot. So here again we will have omega tau, that is 2 omega in this axis, and in this axis we will have phi. So let's say, so at first locate the corner frequency. So when 2 omega tau is equal to 1, so this is the location of corner frequency. So when 2 omega equal to 1, we will have the corner frequency. So next, let's say this is 0.1 and this is 0.01, and this is 10 and this is 100. Similarly here, let's say this is 0.01, this is 0.1, this is 1, this is 10, and this is 100. In the y-axis, here we have, let's say 1, here we have 0.1, and this is 0.01, and this is, let's say 10. So when when 2 omega, so for low frequency asymptote we have 2 omega lies between 0 to 1. So when 2 omega lies between 0 to this, so we will have AR by 6 equal to 1. So this is the low frequency asymptote line, and when 2 omega is greater than 1 and less than infinity, then we have a line so which will pass through this point. So here we will have so this will be minus 1. So this is the high frequency asymptote. So this is high frequency asymptote. So when omega is equal to 0, so we will have AR by 6 equal to 1. When 2 omega tends to infinity, so we will have AR by 6 will be equal to AR by 6 equal to so at the corner frequency 2 omega is equal to 1, and as per the equation number 5, AR by 6 at the corner frequency equal to 1 by under root 2, and that is 0.707. So when 2 omega is equal to 1, so we will have 0.707. So now we can draw the gain plot like this. Similarly, when 2 omega lies between 0 to 1, so the phase shift is 0 degree, and when 2 omega lies between 0 to 1, the phi equal to 0 degree. When 2 omega is equal to 1 at the corner frequency, the phi equal to minus 45 degree. So at this point, so here we will have minus 45 degree, so minus 45 degree. So at this point we will have minus 45 degree when 2 omega tends to infinity. It means phi tends to minus 90 degree. So it means the phase shift at infinity will be low, at infinity will be equal to infinity. So this seems to be like this. So this will be the Bode diagram for the given system. So this is for the 6/2s plus 1. So the same diagram can be plotted as AR by 6 versus omega. So in that case, so the same diagram can be plotted as, so alternate plot. So alternate plot. So in this, the gain plot can be represented as AR by 6 versus omega, and phase plot as AR by 6, phase plot as 5 versus omega. So the only difference is the x-axis. So in the previous plot, the x-axis was omega tau or 2 tau, omega tau or 2 omega, but in this second case the x-axis is omega. So in that case we will have, the only change is so in this case we will have, so in the gain diagram, so this will be the omega x-axis and this will be AR by 6, and let's say this is 10, this is 1 and this is 0.1 and this is 0.01, right? And in the phase plot we will have x-axis as omega and y-axis as phi. So here we will have 0 degree, here we will have minus 45 degree, and here we will have minus 90 degree. So overall, so at low asymptote, when omega tends to 0, the phi tends to 0. When omega tends to infinity, so phi will tends to minus 90, and when omega tends to omega c, and omega c is corner frequency, that is 1/2.5. So this is 0.5, So here we will have, let's say, 0.1, and this is 0.1, and this is let's say 1, and this is 10. So this omega c is 1/2, that is 0.5. So the only difference is that we have the crossover frequency at omega c, that is 0.5, and at this 0.5 the phase shift will be -45 degree. So when omega is equal to omega c, the phase shift will be -45. When omega tends to 0, so we will have 0 degree. When omega tends to infinity, so we will have phi tends to -infinity. So the phase plot will be like this. And if we further extend this plot, in the gain plot, so when omega tends to, so when omega is lies between, so in this case when omega lies between 0 to omega c, right? So the AR by 6 will be equal to AR by C will approach to 1 as omega tends to 0. So when omega c is when omega is greater than omega c, when omega is greater than omega c and tends to infinity, so in that case AR by 6 tends to infinity, but with slope of -1. So when omega tends to 0, we have AR by 6 equal to 1. So this is low frequency asymptote line. Similarly, we can draw the high frequency asymptote line. So for the unit step moving 1 unit in the y ordinate, we have to move 1 unit in the x ordinate. this way, so this way, so this will be the asymptote line. So the slope of high frequency asymptote should be -1, and when omega tends to 0 we have AR/6 equal to 1, and when omega is equal to omega c we have AR/6 equal to 0.707, and when omega tends to infinity we have AR/6 equal to, so this way we can plot the gain plot. That's all for today. Thank you for your attention.